Okay, so the solubility of chromium nitrate, monohydrate, at 15 degrees Celsius is 208 grams per 100 grams of water. Which of the following solutions is saturated? I see you all working, that's great, that's what I intend. Are you going to answer? I'm not ready. First I want to say there's a number of different ways to approach this problem. Does anyone want to share how they're starting the problem? Yeah. Yeah, so a comparison. So maybe taking the ratio, 208 per 100. This is great. This is how I would approach. So we know that we can dissolve, that's not the right thing. We can dissolve 208 grams of the chromium nitrate in 100 grams of water. And so that's a ratio, right? So if we divide that out, we end up with a ratio of 2.08. And so by comparison, we can look at each of the solutions they suggest or asking about and see how it compares to this ratio. What would it mean? What would the ratio look like if the solution is saturated? Compared to this ratio. Higher, lower, same? Same, exactly. So by definition, saturated means we've reached exactly the amount that can dissolve in 100 grams of water. Yes?
So are we assuming that all of this solute is dissolved in that water?
Yes, yeah, this is great. This is questioning salt wash. So you're just assuming that all of that salt is dissolved in that amount of water, no precipitate, no salt at the bottom, and also around the same temperature. So let's look at A. If we divide out 676 grams of the solute and 325 grams of water, what do we get? Yep, 2.08. So right away, we can see that that one's going to be saturated. We can go through and look at the others. I'm not going to divide them all out. But if we look at answer B, and we divide our 83.2 grams of solute per 85 grams of water, we'll end up with a ratio that is 0.97. Okay? So we know it's not saturated. It's not equal to 2.08. Is it unsaturated or supersaturated? Unsaturated, yeah. We could dissolve more into 85 grams of water than what has already been done in that solution. Okay? That make sense? Okay. So sort of along those lines, and going into sort of a like dissolves like territory. We haven't really explicitly used these terms yet in this class. Maybe you heard it in lecture, or recitation. This is lecture. And maybe you've heard it in high school chemistry. Like dissolves like. What this means is that solutes and solvents with similar intermolecular forces should be soluble, should be miscible. And so when we're thinking about whether something can dissolve in a solvent, we need to be considering intermolecular forces of both the solute and the solvent. So this question asks you to rank in order of least soluble to most soluble these 4 compounds in toluene. So toluene is our solvent. And the 4 options are the solutes. Is everyone okay with seeing the screen? Are the fonts big enough, or should I? Okay. All right, which one of these would be least soluble in toluene? C? Methanol? Everyone agree? Yeah, why is that? Yeah. It's the most polar, correct. So methanol has an OH bond. It can do hydrogen bonding. It has a dipole, so it has dipole-dipole interactions, and of course it has dispersion. Toluene is made up of carbon and hydrogen. Those are carbon-hydrogen bonds arranged in a ring. And then this is what we call a methyl group. So it's carbon with 3 hydrogens. But all of that goes to say that there are no dipoles, so no dipole-dipole interactions, and no hydrogen bonding. So this only has dispersion. Okay. Everyone clear with that? All right. So which one would be the most soluble? Hexane. Okay. Hexane, again, only carbons and hydrogens, very similar in terms of the forces that are present. So this is option C, this is option B. Okay, now it gets a little bit more challenging, I think. So we need to figure out which would be sort of second to least soluble. Let's go from least soluble to most. So which is the next least soluble in toluene? Our options now are ethyl aldehyde and hexanol. Yeah. Hexanol? Everyone agree? Why is that? More polar, bigger. Yeah? Has an OH bond. We might actually need to look up the answer. That's not what I have. So here's another way of thinking about this. This long group is all hydrocarbon. Okay. This whole thing is hydrocarbon. The ethyl aldehyde has dipole-dipole, and it has London dispersion. It does not have hydrogen bonding, whereas hexanol does. But now we're looking at a comparison, and this is why I brought this question up. Or think back to butter and water. Okay? Butter has strong intermolecular forces, solid room temperature, and it's got carbon hydrogen. But this has that dipole-dipole. How can we actually figure out the answer? Yeah.
I just remember this but after you hit hexanol,
Uh-huh.
the dipole-dipole interaction becomes weaker because of how drastically larger the hydrocarbon is.
Okay. So dipole-dipole becomes weaker after, we said pentanol. So after 5 carbons. And I mean, according to what I would say here is that hexanol is going to be more soluble in toluene than ethyl aldehyde. But we can actually look up a value and figure this out. So we can verify an answer. So if you look up the dipole moment, and we'll let someone do this. You can get a value, and then the unit on it is Dalton, so you don't necessarily need to know what that means. The uppercase D. And let's compare ethyl aldehyde and hexanol. Okay. We'll come back to that. All right. Does anyone want to volunteer to look it up? We got it. Okay, we're working on it.
Looks like hexanol is 1.6.
1.6 Dalton?
Yeah.
And you got the other one. It might be a little harder. I'm going to go to the next slide. We'll come back to this, okay? Okay. So we looked up the dipole moment of ethyl aldehyde and hexanol. The larger the dipole moment, the more polar the molecule is. Okay. So by comparison, ethyl aldehyde has a greater dipole moment than hexanol, so it should be less soluble in toluene than hexanol. So something that has a low dipole moment should dissolve fairly readily in toluene. So then we're going to have D and then A. Okay. And again, we're increasing that carbon chain, and so that's what makes it less soluble. Did I say it backwards? Oh, we're increasing that carbon chain, so that's what makes it more soluble in toluene. Yes. Oh, no. Yes, good question. So for this one, I love the implication of that question. So I think that recognizing that something with lots of carbon and hydrogen can be more readily dissolved in something that also has more carbon and hydrogen. So lots of CH groups on our toluene here. Lots of CH groups in our hexanol, definitely lots in our hexane. And as we have fewer of those, just looking at the structure, they become less soluble. Does that help? Yeah. And yeah, so the fact that those two were confusing is, I was actually glad that was confusing, because we can use data to show you why something is the way it is. Yes?
I'm just clarifying, you said that the increased dipole moment increases polarity or decreases polarity?
Oh, it just is a definition of. So if something has a greater dipole moment, it is more polar.
Okay, so then it's less soluble?
In toluene, yes.
Oh, okay.
Because toluene has low polarity, low dipole moment.
I see.
Good, thank you. So the opposite solubility would be true in water, right? So the most soluble thing in water, in this case, would be methanol. All right. So let's just do this top question here. I think this might be a little bit more straightforward. Which of these three compounds is most soluble in water? And why? Some people say A. B. C. So most soluble in water, we're going to have high polarity. It'd be good if we have some hydrogen bonding, because that's what water has. Dipole-dipole, and London dispersion. And all three of these molecules have that, okay, but they have the OH group. And because we're increasing the, oh wait, I don't want to do that. We're increasing the hydrocarbon chain in molecule C. We're actually decreasing the polarity of that. Okay? So by comparison, molecule A would be the most soluble in water. Okay? So as we increase hydrocarbon chains, things become less soluble in water. Yes?
Doesn't it have something to do with like the lattice energy too?
Lattice energy. Usually I've only seen lattice energy associated with crystals. Yeah. Compounds.
Like, isn't it when it's like more, like, I'm just like from a common sense standpoint, like, is it like when there's more elements, like, or compounds attached to, like, a figure, doesn't it make it harder for it to be soluble in general?
If it's larger.
Yeah.
If something is larger, is it necessarily less soluble in water? Possibly. Yeah, that's a reasonable assumption if it's organic.
Okay.
So, or by organic, I mean containing lots of carbon and hydrogen. Did you come up with ethyl aldehyde yet?
2.7.
2.7. Yeah. So, which goes to this question. Okay, so same three compounds back of this question we just did. We decided that A was going to be the most soluble in water. If we consider what's going to be most soluble in hexane, that's this molecule. Take a look at the structures. In terms of similarity, C, relabel these A, B, C. C has lots of hydrocarbons, and so it should be more soluble in hexane. Everyone okay with that? Okay. I think there should be some amount of practice on that type of thing in your homework. So take a look at that. Let me know if you have questions on that. We are going to now switch gears a little bit and talk about the solubility of gases. So this is, I think we're now into section 13.3. Okay, so let's say we have a container of water that is sealed at the top. That's what this is showing. And there's some gas above the liquid, okay? Some amount of that gas is going to dissolve into the water, and we're going to have what we call a dynamic equilibrium. We're going to talk about this a lot. Basically, it means that there are gas molecules that are dissolving at the same rate of those that are going back into the gas phase. So they're moving back and forth. That's what the arrows are trying to show. If we increase the pressure on the gas above the liquid, so we're going to increase the pressure, and we're going to do that according to this figure by decreasing the volume, so PV equals nRT. We are now increasing the pressure on the gas above that solution. And so that's going to throw off the equilibrium, and that increased pressure is going to force more gas molecules to dissolve. And then we get to equilibrium again. Right? So same rate, things going out of solution as things going into solution. This slide is not in there in your notes. Is that what you're going to say? Yeah, I put this in late, sorry. If you Google gas solubility, this is like the third picture that shows up. Okay? My apologies. But I want you to have this picture in your mind. Okay, so we have gas over a liquid. We're thinking about how pressure affects solubility. Excuse me. The relationship between pressure and solubility is given by an equation that we refer to as Henry's law. In Henry's law, we have that the solubility given in moles per liter of the gas is equal to some constant K, the Henry's law constant, times the partial pressure of that gas over the solution. So just for one unit clarification here, this is kind of unclear. So the solubility is moles of solute per liter of solution. Okay? And the Henry's law, the constant, is only going to be for a given gas in a given solvent at a given temperature. Okay. So those three things matter. You change the solvent, the constant's going to change. You change the temperature, constant changes. Okay. But for gases, we can see a linear relationship between the solubility and the partial pressure. All right, that's essentially what this equation is showing. Okay, so if we recall that the equation for a line is given as y equals mx plus b, that's essentially what Henry's law is saying, where our intercept b is 0. Okay, so if we plot solubility on y, our slope is going to be equal to k, and the pressure on x. Okay. I don't know that you're necessarily going to need to do any calculations with that, but I'd just like you to see that relationship. It's linear. Okay, so if we increase the pressure, the solubility of a gas increases. I might have also changed this slide on you as well. There were some numbers in the middle of these two graphs, and I couldn't figure out why I had written those. So I've deleted them on my version. I'm sure they were the solubility of something, but I don't recall what, and it's not in my notes. Okay. So the solubility of the different gases now. So this first chart just showed the solubility of helium. Take a look at this solubility chart here. Solubility on Y, partial pressure on X. What's the trend in the increasing slopes with the different gases? What's changing about the gases? Well, yes, the solubility is changing, thank you. Yeah? The molecular weight, yes. So as the molecular weight is increasing, we see an increase in K and the slope. This is all to say that the molecular weight does play a role. The nature of the solvent does play a role in how soluble it is. Okay. Now what about the solubility of gases with change in temperature? So we saw in our demo, the way we made our sodium concentrated, supersaturated sodium acetate solution was we increased the temperature. And that allowed more solvent to dissolve, more solute to dissolve. But look at this figure for the gases. As we increase the temperature along our x-axis, the solubility of those gases decreases. And you probably noticed this, but maybe you didn't notice it. Right? If you boil a pot of water, you initially see some small bubbles that escape from that water. If you're slowly increasing the temperature of that water, now you have dissolved gases that are escaping. Once you reach the boiling point, those bubbles are made up of the gas that is water gas, water vapor. But before that, before you get to the boiling point, you're probably getting rid of any dissolved carbon dioxide, nitrogen, various other things. Okay? So I guess what we can say here with the solubility of gases is pretty predictable. We know if we increase the pressure, we're going to increase the solubility for a gas. If we increase the temperature, we're going to decrease the solubility for the gas. The same is not true for solutes that are solid, or liquid, for that matter. This chart shows the solubility of a number of different salts with increasing temperature. And if you just take a look at a few of these, so here's our calcium chloride. The solubility of that increases drastically with increasing temperature. Take a look here at cerium sulfate. The solubility of that salt actually decreases with increasing temperature. So it's actually kind of counter to what you might expect. If you're thinking about, and I think the textbook invokes this example, if you're trying to clean something, oftentimes you'll use warm water to help dissolve things. But that's not always the case, okay? It's not always what is useful. I don't know why you would be trying to dissolve cerium sulfate, but it wouldn't work at higher temperature. Okay. Questions on any of that? Yeah.
Why it does that, or is it just because it does that?
So why does the solubility decrease at higher temperatures? I actually don't know if I know off the top of my head. And why they're so different for different salts. Let me take a look at that, think about that, and try to get back to you on Friday. Yeah. My guess is the answer is either has to do something with thermodynamics. So, but I don't want to misspeak, so I will pause with that. Any other questions? Okay. Okay. So let's now get to a somewhat more boring but also necessary discussion on concentration units. We are going to be using lots of different types of units for concentration in this course. In the lab, you will most likely see molarity. You may sometimes see molality. That's going to come up when you do a freezing point depression lab? Okay. So you'll be using molality in that case. So I don't necessarily want to go over each and every one of these sets of units, but I do want to point out a couple of things. So molarity, again, very common, moles of solute per liter of solution. Right? Pay attention to what that full description of the unit, liters of solution. Okay? That includes both solute and solvent. Moles of the solute, just the solute, right? So if we have, for instance, in mass percent, we're looking at the mass of the solute over the mass of the solution. So mass of the solution is going to be equal to the mass of the solute plus the mass of the solvent. Okay? That's going to be important when you're thinking about changing between concentration units, which, of course, will come up on the exam. The other unit that you'll see a lot is parts per million. And I guess when I say see a lot, if you're staying up to date on various issues regarding environmental contaminants, or even greenhouse gases, oftentimes we're using parts per million units. Sometimes parts per billion for our really toxic substances. And so these units are important. I want you to know these definitions: mass of solute per mass of solution times 10 to the 6 for parts per million. And then for parts per billion, it's times 10 to the 9. Okay? So that's the times 10 to the 9 is accounting for the difference in that billion factor. So that's the number of zeros in the billion. But there's another unit, there's another way of thinking about parts per million and parts per billion that is, to me, more useful, partially because I do analytical chemistry and almost all of that is in aqueous solution. So if we assume we're at room temperature, RT, we can basically say that the density of water is equal to 1 gram per milliliter, right? Close enough. 0.999 to something, I don't know, whatever. And if we're working in really small quantities, like micrograms or even milligrams of a solute, then if we're looking at what a massive solution means, the mass of the solute matters so little. Okay, again, really small amounts of solute, that adding to a mass of solvent in large quantity makes very little difference. And if you're thinking about significant figures, that's the reason why. Okay, so another way we can then think about mass or parts per million is units of milligrams of solute per liter of solution. Okay. Milligrams per liter. So again, assuming the density is 1 for water, assuming that the mass of the solute matters incredibly little, significant figure-wise, we can make this assumption. I like this unit. I think it's easier for me to think about. But I also, like I said, I want you to know this other definition. We will be using that as well. Okay. Okay, so let's just take a brief aside here. Who knows what PFAS chemicals are? Heard of it? Forever chemicals, right? So the EPA recently released a notice that PFAS chemicals are now toxic at very, very low levels. And if I remember correctly, it's at the parts per trillion level, which is even smaller than parts per billion. And this is incredibly interesting to me as an analytical chemist, because that means that we're going to have to be able to detect those types of chemicals at the parts per trillion level. Parts per billion itself, I think the analogy is you think of one drop of water in an Olympic-sized swimming pool. That's 1 part per billion. Parts per trillion is even smaller. So we have to be able to detect that. That's an analytical chemistry challenge. If you're interested in that, talk to me. Other than that, enjoy lab or recitation tomorrow, and I'll see you on Friday.